So I'd like to welcome today's speaker, Baptiste Rognerud, who's gonna give us a talk on combinatorics of torsion pairs, an open question. So thank you very much, Baptiste, and you can start whenever you're ready.
Yeah, thank you. So thank you for the invitation. It's really a pleasure to speak here. So yeah, the title is Combinatorics of Torsion Pairs, an open question. And I chose this title because I wanted to put some algebra in it. Actually, I'm not going to speak about algebra, so I'm sorry. But I will still start with torsion pairs because even if the paper that we wrote with Yongle Luo is not about algebra and torsion pairs, it's the only thing we thought about during the whole time of writing this paper. So it's really motivated by this setting. Okay, so I will start by the open question, so an open question about torsion pairs. And maybe I will try to find a better position for myself. Yes. Okay, I assume that probably you know a lot about torsion pairs, but let's recall what I have in mind. So A will be an abelian category. And yeah, for example, this would be the category of finite dimensional module over a finite dimensional algebra, so, for example. And then a torsion pair is, first of all, a pair of two subcategories. So a pair of full additive subcategories of my abelian category. And it must satisfy two properties. So the first one is very easy. There is no morphism from the torsion part to the torsion-free part. Okay. And the second one is like a maximality property. And there are many ways to write it, but maybe the best, or the one I like is every object in your abelian category should be stuck between a torsion and a torsion-free object. So there is a short exact sequence like this, where this is in the torsion part, and this is in the torsion-free part. So this is like a maximality property for these two. And when you have this property, you say that, oh, there is a missing part. So this is a torsion pair. When you have these two properties. And of course, the examples that we should have in mind, the original example is when you take A to be the category of abelian groups, finitely generated or not, then you could take T to be the torsion abelian group, and F to be the torsion-free abelian group. And then it is known that every abelian group has the largest torsion subgroup such that the quotient is torsion-free. And so this is, the torsion pairs is like an axiomatization of this theorem about abelian groups. But as every good axiomatization, there are many more examples. So there are stupid examples like this one. So you could take the torsion part to be the full abelian category and the torsion-free part to be just the zero category. And then, yeah, this is a torsion pair. You could choose the other stupid example as well. And in representation theory of finite dimensional algebras, there are many more interesting examples. And maybe the best way to explain it is saying that there is a bijection between torsion pairs in the module category of so finite dimensional module over finite dimensional algebra plus a decoration. So the decoration would be something called functorially finite. And if you don't know what it is, it's not a big deal, but it's only part of the torsion pairs. And this is in bijection with the so-called support tau tilting module. And this bijection is a theorem of Adachi Yama-Reiten in 2012. So I will not explain the terminology because I will not need it, but support tau tilting or tau tilting theory is like the largest topic in representation theory of finite dimensional algebra for like the last 15 years. So this bijection basically told us that we should know almost everything about torsion pairs. So this is very well studied. Very well studied. And the field has started to, maybe it's not finished, but we know many, many results. So we know a lot about torsion pairs. Okay. But we don't know everything. So I will ask a question, a very easy question that we don't know how to solve. But before setting the question, I need to introduce a little bit more notation and more properties. So the first thing that we need to know is, in general, there are infinitely many torsion pairs. So it's kind of a mess. So we would like a structure on it. And this is a nice thing because the torsion pairs, they form a poset. At least up to set theoretical problems, because probably we don't know if it's a set, but yeah, if we don't care about sets problem, it's a poset for the partial ordering like this. You will say that a pair is smaller than another one if there is an inclusion between the category of torsion and an inclusion in the other way between the category, the torsion-free part. Okay, so this is the first easy statement. This infinite information can be ordered using this partial order. Actually, the first inclusion implies the second inclusion, and conversely. But okay. So this is the first information. And the second information is about the missing part of the bijection, this non-functorially finite torsion pairs. If you don't want to think about them, you can work with algebra having only finitely many torsion pairs. And we will give a name to this algebra. So we will say that an algebra A is tau tilting finite. The number of torsion pairs is finite. And in this case, it is known that all torsion pairs are functorially finite. So in particular, studying the tau tilting theory is really the same thing as studying the torsion pairs. So study tau tilting theory is the same as to study torsion pairs. Okay, so this is really the setting that I have in mind. I don't really like this other part, this non-functorially finite. And it's because I like to do combinatorics. So yeah, some easy, not easy, some just facts. So the first fact is from the combinatorial point of view, these posets, they are quite interesting. So posets of torsion pairs of tau tilting finite algebra or they have interesting combinatorics. Okay, so this is the first fact. And conversely, many posets with interesting combinatorics can be realized as poset of torsion class. So this is the an if and only if statement. So many interesting posets can be realized like this. So for example, yeah, I just give names. If you don't know the name, it's also not a big deal. But for example, there is the so-called Tamari lattice. This would be the poset of torsion pairs for a path algebra of the type A quiver with linear orientation. So this would be the first example. There is a large class, which is the so-called Cambrian lattices, which is due to reading. And here you take you replace the type A quiver by any Dinkling quiver. Okay, so this is another example. Then you have the Wick-Brugger order.
And whatever is the orientation of these quivers?
Yeah,
or...
exactly. Right. So the Cambrian lattices, they depend on the choice of a Coxeter element.
Okay.
So
this
each
has
orientation,
to do with this scissor-double elements.
Exactly. Yeah, exactly. Exactly.
All right.
And the Wick-Brugger, here there is no orientation because you need to take the pre-projective of Dinking type. So no orientation for the Wick-Brugger order. And there are many more. Yeah. Some they have names, some there are many more. Okay. And once you can realize your favorite poset as a lattice of torsion pairs, this is quite nice because then you can use algebra and representation theory to prove stuffs. So this will, in general, leads to clean, easy. Well, if you like algebra, if you don't like algebra, you don't say easy, you say formal, maybe proof. So instead of working with a complicated combinatorial object, you just work with category theory, and this is in general, very easy proof. So this is really something that is good if you can realize your poset like this. And here comes the question. So the question is, can we characterize the poset of torsion pairs? So can we characterize the poset L isomorphic to torsion pairs of the finite dimensional algebra? And because this is way too complicated, so let's focus on finite posets, so of tau tilting finite algebras. And okay, so this is the question. And spoiler alert, we don't know the answer. But why do we need such so yeah, why do we care? So if we could answer this question, this would be very good for combinatorics because then we would have a large class of posets on which we can apply tools from algebra. So large class of posets on which we can apply representation theory. So this is for combinatorics, and for representation theory, this is also quite useful because if you have such a nice characterization, like a combinatorial characterization, then you could play with your computer to test ideas and conjectures on a large family of on a large family of examples. So easy access to a large list of examples on which we could test conjectures and ideas. And yeah, I should say that actually using some algebraic computer program, you can produce an algebra. You can do mutation of tau tilting module. So in theory, you can compute the lattice of torsion pairs of tau tilting finite algebra. But every time it's like a hard work. So it's difficult to find a large lattice of torsion pairs using the computer. This is really hard work. So if we have such a characterization, this would be very nice. Oh, okay. I was a little bit okay. So yeah, maybe we skip this one for the moment. Okay. So how to answer the question? So to answer the question is it should be easy. So if we know enough, on tau tilting theory, we should find an answer. So what do we know?
Sorry, I wanted to ask a question.
Yes.
Maybe I missed it because my connection is going on and off, but did you give an example of a poset that you know that would not appear?
Yeah, I will give some. I will first give a list of property that they must have.
Okay.
And then I will give example of poset where we know that they will not appear.
Okay,
and,
thank you.
Okay, so the more you know about tau tilting theory, the more difficult it is to find a counterexample. So what do we know? Okay, so theorem. So there is, yeah, it's a theorem of many people, starting from Adachi, Yama, Rayton. So Adachi, Yama, Rayton to probably the most important paper for me is Demonet, Yama, Rayton, Reading, Thomas. So what do we know about torsion pairs of tau tilting finite algebra? Well, first, it's not only a poset, it's a lattice. So what does it mean? It means that you have like a GCD and a LCM in your lattice. So it's a poset with GCD and LCM. So it's much nicer than an arbitrary poset, okay? Then this lattice, it has two deep properties that one of them I will not explain, one of them I will explain. So it's the first is it is a semi-distributive lattice. So this I will explain later because it is not so difficult. And the third property is it is a so-called congruence uniform lattice. So this I will not explain because this is much more technical. And I should say that this is actually stronger than this. So the property number 3 actually imply the property number 2. So this one is a deep property of a lattice. Okay, so these are for the general result on torsion pairs. There is one that is true for tau tilting finite and not for arbitrary algebra. This is about the mutation of tau tilting theory. So there is a mutation of tau tilting module, of support tau tilting module, and this mutation implies that the Hasse diagram of the poset is called regular. So what does it mean? It means that so you have your tau tilting module, then you can mutate at every summons, and every mutation gives you an increasing relation or a decreasing relation. Okay, so you have a number of arrows that go up, let's say n1, and a number of arrows that go down, let's say n2. And then this is always the number of summons of your support tau tilting module. This is always the number of simple modules. So this should be the same for every element of your poset. Okay, so this property is called regularity. And I think that's it for the easy one. There is a number 5 that is more tricky. But maybe I want to write it. So only for the experts. Whenever you have a torsion pair, you have a notion of wide subcategories, and there is a lattice of wide subcategory. So the lattice of torsion pairs, it has an associated lattice of wide subcategory. And this has a poset meaning, so we could define the number 5 in terms of posets. And this is actually related to the topology of the poset, the number 5. But yeah, maybe I skip it. But yeah, so I think that's it for what is known for this poset in full generality. And the claim is 1 to 5 does not characterize the lattice of torsion pairs. And yeah, so I think maybe we are missing something. So maybe we are missing something, but these 5 properties that are the 5 known properties, they are not enough to characterize the lattice of torsion pairs. And maybe what I will try to answer today is how sporadic are the counterexamples. Counterexample. And if we take 1 to 5, I don't know, but for the 3 first property, this is really not sporadic, and this is what we will see in the rest of the talk. So I will construct infinitely many posets that satisfy 1, 2, and 3 and are not poset of torsion classes or torsion pairs. Maybe I show an example of a poset satisfying 1 to 5, and which is not a poset of torsion pairs. So I have to go down. Yes, this one. So this example. So if you don't like the rest of the talk, you can think about it. This example is the third of the so-called Hochschild lattices. And it's not a lattice of torsion class. So the first one, it's okay. This one, it's okay. This one, that is an intermediate step, is also okay. But this one is not a lattice of those torsion pairs. Maybe I can explain at the end if you want, but it has all the good properties. So it has 1 to 5, but it's not. Okay, so let's go back to this. And yeah, no, okay, the picture is here. Okay, so yeah, the example that I have in mind, yeah, lattices, instead of coming from algebra, they come from topology, and they come from a field of topology which is called homotopical combinatorics. Here is an example. I go up. Yeah, here is an example of lattice that we will meet in this homotopical combinatorics. It's also not a lattice of torsion pairs. Maybe this one is easier than the other one because it's not regular. So yeah, maybe this one is easier. Yeah. Okay, so what is homotopical combinatorics? So homotopical combinatorics. So I should say that I did not invent the terminology. I'm not sure it's a good terminology, but anyway. So the homotopical combinatorics, oh, I need my notes. This is more or less new field starting in 2015 and involving mainly the work of Bloomberg, Hill, Holmes, Balchin, and others. So they are really algebraic topologists working in homotopy theory. And the main result in homotopical combinatorics is this theorem. So it's a theorem which is due to Bloomberg and Hill in 2015. And I think the last piece has been done in 2021. So many more mathematicians. And this theorem, I will be quite vague, but yeah, let's write the theorem. So it's a theorem about finite groups. So you choose your favorite finite group, and then you have an equivalence of categories between a complicated category and a very easy one. So there is an equivalence of category so between one category, which is the so-called homotopy category of n infinity G operad. So this is the complicated one. And another category, which is called the category of G transfer system. Between the homotopy category of G n infinity operad and another category. And the other category is just a poset. It's a poset of G transfer system. And because you want a category, so you see the poset as a category. Good, as a category. Okay, so this is the main motivation. On one side, you have a very complicated object, which is the so-called n infinity operad. So yeah, I'm not sure I want to explain what is an n infinity operad, because to be honest, I'm not sure I understand very well what is an n infinity operad, but you know that in topology, they like this kind of multiplicative law that is only associative up to higher homotopy. So this would be an algebra over an A infinity operad. If you want associative and commutativity up to higher homotopy, you will have a notion of E infinity operad. Okay, so E is for everything. And now you have a finite group. Okay, so you want a G equivariant version of E infinity operad. So you have associativity, commutativity, and group action, everything up to homotopy. And an N infinity operad is a particular example of this kind of object. And so that there is a property on the fixed point of the operads, and in particular, an algebra over such an operad. So it would be associative up to homotopy, commutative up to homotopy, with a group action up to homotopy. But you would also have something more related to the non-empty fixed point of the operad. So you would have, so an algebra X, it has some kind of induction map. And this induction map, they are called norm maps. So the N here is for norm. Going like for group theory, like an induction from group theory. So going from the smaller group to the larger group. So it's like a Mackey functor, if you know what it means. But you don't need all the subgroups, so only for some subgroup K smaller than H. So it's like a partial Mackey functor. A partial Mackey functor. So yeah, very complicated object that I would not dare to try to classify. But using this theorem, this very complicated object is related to something else, just a poset. So what is a G transfer system? Okay. So a G transfer system this is much easier. So I want a name. So yeah, I choose a partial order like this. A G transfer system is a poset on the subgroup of G that should satisfy it should satisfy some condition, and the conditions are also fairly easy. So first of all, if a subgroup is smaller for this transfer system than another one, then it should be a subgroup of the other one. In other words, this is a subposet of just the classical inclusion of subgroups. Okay, so this is the first condition. Then there is a condition involving the group G. So if you have a subgroup that is smaller than another one for your transfer system, then when you conjugate the groups, you should still respect this relation. So this should be true for any element of the group. And the last property is probably the most technical one, but because you do a little bit of algebra, this will not be so technical. So if you take three groups, H smaller than K and L smaller than K, then you can do a pullback in the category of the subgroups. So what is a pullback? Well, it's just the intersection. Yes. So every time you have three groups, you can do a pullback like this. And every time you have a pullback diagram like this, you want if the lower part is comparable for your transfer system, the upper part should also be comparable for your transfer system. So this is the third condition. So this is like a closure by pullback. And the condition 2 is like a closure by conjugacy. So if you think about torsion classes is closed under extension and closed under quotient. And here we also have two closure properties. Okay, and so this is a transfer system, and we need a category of transfer system. So we need a poset of transfer system. But because there is a poset of posets, this would be, so this is a poset for the relation being a subposet. Okay, and okay, so this is it. This is the theorem. this very complicated equivariant topological object, n infinity operad, up to homotopy, is nothing but a very simple combinatorial object on the subgroup of G. And I would not dare to classify n infinity operad, but this thing, I can try at least. I can try to classify this kind of posets. So let's do some remarks and examples. First remark, if your group is abelian, well, there is no conjugacy in an abelian group. So the condition 2 is empty. Okay, so it's only 2 conditions instead of 3 in this case. And in particular, we see that the group does not play anymore, it does not occur anymore in the definition, only the poset of subgroups, or more precisely, because we take pullback in the condition 3, the lattice of subgroup. So because of this, we can define a more general notion starting with a finite lattice. So I just quickly write the definition. I will just copy 1 and 3. So if you take a finite lattice, then we can define a transfer system on it. So a transfer system on L is a subposet of L, which is closed by pullback. So every time you have a pullback diagram like this, if the lower part is in the transfer system, the upper part is also in the transfer system. Okay, so this is just to remove the group of the picture and to have a more general setting. And it's not only to simplify the thing, there is also another motivation. So the transfer system associated to finite lattices, they are related to Quillen model structure on the lattice, are deeply related to Quillen model structure. On the finite lattice L that you view as a finite category. So we have 2 motivations to classify the transfer system. One coming from model structure, the other coming from G equivariant topology. Okay, so this is this is the main objective of what they call homotopical combinatorics. So the objective of this field, homotopical combinatorics, is to understand the transfer system associated to finite lattices. Transfer system associated to finite lattices. At least count them or find some property that they have. Okay. So examples. The simplest non-trivial example occur when you take a cyclic P group. So a cyclic P group with P to the n elements. Then the subgroup of G as a poset is just a total order. Okay. So what is a transfer system on a total order? So a transfer system on a total order. So you need to choose a subposet of a total order. So how do you choose a subposet of a total order? Well, it's fairly easy. You need to decide, you take two integers, and you need to decide if they are comparable or not. And because you want a subposet of the total order, you just need to decide if an integer I is smaller for the classical ordering than an integer j, you need to decide if you put it in your subposet or not. That's it. And then maybe you need to take transitive closure at the end. So this is a subposet. You just decide which of the pairs I smaller than j are in your subposet, and you take transitive closure. So subposet is very weak condition, but we need a subposet that is closed under pullback. Okay. So what is a pullback diagram in this case? So you take three integers. So I, j, k, and they should be like this. So I should be smaller than j, k should be smaller than j. Then you want to take the pullback, but the pullback in this case is just taking the minimal element of the two. Okay, so if the minimal element of the two is k, here you find the relation k smaller than k. And because the subposet is reflexive, there is no condition here. So there is a condition only if you have this setting. So you have I smaller than k, smaller than j. And then if the lower part is in your transfer system R, the upper part must be in your transfer system. So having a long arrow like this imposes to have a small arrow for every element k between I and j. And this is a transfer system for this total order. So if we do quickly an example with three elements, so 0, 1, 2, what can you do? Well, first you can choose zero relation. So this would be the equality relation. And at the opposite of the spectrum, you can choose every relation. And this will also give a transfer system. And then you can do something smaller. You can choose only the small relation 1 to 2. And this would be a transfer system. And you can choose the relation 0 to 1. This would be a transfer system. Or you can try to choose the long relation 0 to 2. But this long relation imposes that you also have a small relation like this. And so the poset of transfer system for CP2 is this pentagonal poset. And yeah, maybe you know what is this pentagonal poset. So there is a theorem. The theorem is due to Balchin, Barnes, and Roytsan in 2021. And we reprove it with Jungler in 2024 with a very simple proof. So the poset of transfer system for CP to the n is isomorphic to the Tamari lattice, which in torsion classes is the lattice of torsion pairs of type equivalent with linear orientation. Okay, so this is the main, I think this is the best result in homotopical combinatorics, the cleanest result. So the number of n infinity operad for this cyclic group is a Catalan number. Okay, so this is like the good result, and the very bad result in homotopical combinatorics.
Sorry, did
yeah.
you give explicit bijection between the tilting, super tilting modules and transfer systems?
Yeah, exactly.
Right.
So yeah, so this kind of condition that is here.
It's
so if you
closeness under equations, right?
Yeah, it's really related to this. So I think the best is to. So you see that. Yeah. So here it's CP to the n, and here it's the path algebra with n elements. But CP to the n is the lattice of subgroup
right.
is one more. Okay.
Right.
So the torsion class, there is one less indices. So in some sense, this is related to the tilting part of the torsion class.
Right. Yeah. So you include always the projective injective and everything.
Yeah, exactly. And yeah, the bijection is very explicit.
Right.
So this you take an up to the transfer system, and if you take an up, you find something related to binary tree. Trees, and binary trees are related to tilting module.
Yeah, of course.
So it's really more related to tilting than torsion classes.
Right.
But in this setting, torsion classes and tilting, they also
they coincide
isomorphic. So yeah, it's a very explicit bijection that you can follow. If you know very well the algebraic part, you can follow the combinatorial bijection to find this algebraic meaning of this transfer. Yeah, you can find an algebraic meaning. Okay, so yeah, this was the very nice result, and let's move to the very bad result. So you also take a very simple group. So here, instead of taking a cyclic P group, you take a product. Well, it's also a cyclic group, but you take a product of cyclic P group with P elements, but for different prime numbers. So it's like a square-free abelian groups. Square-free abelian group. And here, the lattice of subgroup is also very simple. The lattice of subgroup is just the subset of n. So it's a Boolean lattice, the subset of n. And the starting point is like this. And then you have the cube. And then so on. I will not draw the cube with the hypercube. Okay, and the number of transfer system. So before our work, only the first 4 were known. So this is 1, 2, 10. So this 10 is the same as the picture I drew before. So this is the lattice of transfer system for the CP cross CQ with P and Q two distinct prime numbers. So there are 10 of them. And the next one, it's actually, so the first 3 are like exercises. The next one is it's a paper. It's 450. And before our work, the next term was not known. And using the computer, we found like 5 million for the next one. And then we found a lower bound for so we did not find the next numbers, but we found a lower bound which is 2 to the 55, 2 to the 51, then 2 to the 126, and 2 to the 393. And yeah, basically it means that it will be very hard to classify transfer system. So it will be very hard to classify the G transfer system. And if you look at the first papers in homotopical combinatorics, there was more or less this idea that maybe we could classify transfer system for every abelian groups. But I think it would be very hard. Okay, so this is like a very good result and a very bad result. So there are even if it's a very simple combinatorial object, to count transfer system is a difficult task. Okay, and yes, a theorem. So this is a theorem that we proved with Jungler in 2024. Okay, so we take any lattice, finite, and then we are able to see, well, this was known before. First of all, it is a lattice. The poset of transfer system is always a lattice. So this was known before. Before us, it's very easy. Okay, then it is semi-distributive. Okay. Then it is congruence uniform. So it's like the 1, 2, 3 of torsion classes. The third part of the theorem is about counterexample to my question. So first of all, the map sending the lattice L to the lattice of transfer system is injective. So it means that this will produce as many examples of lattices satisfying 1, 2, and 3 as you want. So it's a proper class of lattices satisfying 1, 2, and 3. And yeah, maybe the part number 5. Oh, so these are not the same 4 and 5. So let's say A and B. And then if a lattice of transfer system is isomorphic to a lattice of torsion pairs of a finite dimensional algebra, it means that L is a total order. And so the transfer system of L is a Tamari lattice. And so the only lattice of torsion pairs that you will realize using transfer system is the lattice of torsion pairs of type equivalent with linear orientation. So infinitely many counterexample to 1, 3 characterize torsion pairs. So these 3 properties, they are really, really far from characterizing torsion pairs. And I think it was not expected. Yeah, but I think, yeah, I only have 5 minutes. So yeah, I think it was not expecting. There is a theorem which is called the fundamental theorem. Okay. Fundamental theorem of finite semi-distributive lattices, which is due to oh, sorry, I don't remember. To Reading, Thomas, and someone else. I'm sorry, I don't remember, but yeah, very recent theorem. And I will not write the theorem, but in the introduction, they say that we should think as semi-distributive lattices as torsion pairs in an abelian category. And yeah, they construct this characterization of semi-distributive lattices with intuition, the theory of torsion classes. But in fact, there are infinitely many examples that do not come from torsion classes. So the intuition is still good. So yeah, the intuition is still good, but we have to be careful because they are not lattices of torsion classes. Yeah, maybe I wanted to explain semi-distributivity, but maybe I skip. And yeah, I just to using 5 minutes or 2 minutes. So we have different corollaries of the theorem. The theorem is actually not difficult to prove, and we have different corollaries. Semi-distributivity is very nice because it allows you to have a nice algorithm to compute. So we have a nice algorithm to compute the number of transfer systems of a given lattice. So it's a graph theoretical algorithm. And it's using semi-distributivity that we were able to compute this number here, and also to find the lower bound here and here and here. So this is a consequence of semi-distributivity. And yes, we also have more structural results. On the lattice of transfer system, for example, on the lattice of congruencies and so on, that are slightly more technical. So maybe I don't explain, but so there is a, if you know in tau tilting theory, there is a brick labeling. Here we also have something like a brick labeling. So if I go back to the picture, you see that every edge has a label. So this is the equivalence of a brick labeling, which is actually a consequence of semi-distributivity. So yeah, we have many nice consequences of this theorem. And yeah, maybe I stop here. Thank you.
Thank you very much. It was a very nice talk. Are there any questions?
Yes. So I have one first question that actually has to do with this brick labeling that you were mentioning. So in this paper by Demonier, Yama, Reading, Writing, and Thomas, they have this quotient, right? I mean, they quotient an algebra by an ideal, and they say, well,
Yeah.
you have some relationship. So do you have something similar here?
We don't know yet. Yeah, we have something similar. We know how to construct the quotient of the lattice by congruencies. So we have a full understanding of the lattice of congruencies. So in theory, we have a full understanding of the quotients.
Right.
But yeah, so in this paper, they look like, so they start with an algebra and they choose an ideal and they do the quotient of the algebra by the ideal, and you have relation for the lattice of torsion classes. This we don't have.
Right.
I don't know what is going on.
Right. What would it mean to have a quotient of a lattice and then look at...
So you could take a quotient of the lattice L and then look at transfer system of the quotient, and maybe there is a relation with the quotient of the transfer system, but this we don't have yet. We don't know if it's working very well or not. Yeah, we also don't know if the map sending a lattice to the lattice of transfer system. We know it's injective, but we don't know if it's functorial or not. Maybe it's not, but yeah, we don't know.
Right.
Are there any more questions?
Yeah, I wanted to ask you about the correspondence you mentioned between the sheet transfer posets and the model structures on the posets.
Oh yes. So yes, this part. So yes. So this part, yeah. So the model structure, usually you start by looking at something called a weak factorization system.
Yeah.
I don't know. Okay, so you look at weak factorization system on your category, on your given category. And the weak factorization system, you have a left part and a right part. And for a lattice, the right part is exactly a transfer system. And so the left part would be the solution of the lifting property with respect to the left part. So usually the right part is closed under composition, it's closed under pullback, it's closed under isomorphism and so on. And if you write what it means for a lattice, being closed under composition means you take it means being closed by transitivity. To contain isomorphism, it means to contain only the reflexive relation. And so you end up with exactly the definition of a transfer system. There is also this retract property, but the retract property for a lattice is always the only retract are identity. So yeah, in the end, the transfer system is only the right part of a weak factorization system, and it determines the left part. And the model structure, then you have yes, you need to take an interval and look at the so-called weak equivalencies, and requires this 2 out of 3 property.
Are there any more questions?
I do have yet another question that has to do with this example that you showed about Hochschild
Yeah.
posets, lattices. So how these are related with Hochschild homology or cohomology?
I
Or
don't
not
know.
really? I mean, or why the name comes
yeah,
from?
I don't know. I don't remember well the story, but there is something called a Hochschild polytope that
Okay.
has been introduced a long time ago. That must be related to Hochschild in some sense, but I don't know. And
Okay.
this is an orientation on the edges of the Hochschild polytope.
Okay.
But yeah, I don't know what is the relation with.
Yeah.
This has to do with some cellular complex, but yeah, I don't
It
remember.
doesn't matter. It was just a silly
Yeah,
question.
but it's quite funny. So yeah, can you see why it's not a lattice of torsion pairs? This is very tricky. It took me a while to.
I mean, what I see in the maybe is that you have two squares next to each other. This looks odd in a way, but
Yeah,
I don't know
maybe.
if this is.
Yeah, but yeah. So I think
So
you
how you
could
see
find.
it?
Yeah, there are 2 ways. You could find the quiver. So there is a paper by Kaze where he explained how to find the quiver starting from the poset.
Right. Yeah, using the
And
layer.
here
Yeah.
the quiver should be this. And
Right.
and the poset is not a product.
No.
So this is one way. And the other way is so here you have 0, S1, S2, S3. Okay. And you can look at the Serre subcategories containing 2 simples. So the Serre category containing 2 simples, you have one here.
Yeah.
So it's a pentagon. There is one here. It's a square. There is one here. It's a square. So 2 square, 1 pentagon. And then you use Rasso's reduction theorem. So the support tau tilting module that have a given simple in the support is the same as the support tau tilting module in the Serre subcategory. So in the algebra A modulo the corresponding idempotent. And this should be the same as the support tau tilting module containing one given projective indecomposable as direct summand. So there is you need to look at the upper part of the picture. So yeah, let's do in red. So the upper part, you look at the projective indecomposable, they are like this. And then the interval having the projective indecomposable as direct summand, you have this one, which is a square. You have this upper one, which is a pentagon, and this one, which is a pentagon. So you have
Right,
two
and it's not
pentagons and one
symmetric.
square,
No.
and the other one has two square and one pentagon, so it does not work. So here
I see.
the key is this Hasso reduction
Right.
theorem.
Right.
So there is like so the lattice of torsion pairs, they have like a symmetry between the top and the bottom. They do not need to be self-dual, but they have
no, but you
weird
have this symmetry. Yeah, but this symmetry comes from torsion classes and torsion-free classes, right? And
I don't know if it's really that.
Okay.
I don't know.
Because,
maybe, but
yeah, I mean, there is this paper, this result by Auslander and Smalo saying that torsion class is functorially finite if and only if the torsion-free class is functorially finite. And then you have this bijection, and so you would have a support minus tilting objects with support tilting objects.
Yeah. So,
Yeah.
but yeah. But I'm not sure that this symmetry is a consequence of this. This is
right.
Yeah. I don't know.
Yeah.
But this is the part I don't really know how to. What is the lattice version of this Hasso reduction theorem? This I don't know.
I see. I mean, and you said that you have 4 and 5, 4 or 5 properties which had to do with these wide subcategories, right?
Yes. So the property number 5 is this has to do with wide subcategory. Yeah. So where is it? Yeah.
So and you don't know about transfer systems and these other 4 and 5.
So this is a work in progress.
Okay.
So the property number 5. So any congruence uniform lattice, you can define a poset. Starting with the congruence uniform lattice, you can define a poset, and this going from the lattice to this poset is really what you do when you go from torsion class to wide subcategory. So there is a combinatorial version of this number 5. And if you do it for transfer system, it seems that you don't have a lattice. You only have a mid-semi-lattice.
I see.
But we did not prove it yet, but it seems that this is what is going on.
Right.
It's not a lattice, only a mid-semi-lattice. And for this Hochschild thing, this is a lattice. So this Hochschild posets, they satisfy 1 to 5.
All right. Yeah.
So there is an explicit description of what is the wide subcategory of this associated to these posets.
Right.
So these one are quite.
And these wide subcategories, in a way, are related with exactly the Hasso.
Yeah, I don't know. This is really related to the brick labeling.
Right. But the brick labeling, so the bricks are literally the symbols in the wide subcategories, right?
Yeah, exactly. So this is what you do. Instead of looking at the torsion class generated by your bricks, your semi-brick, you take just the wide subcategory generated by, and you look at this inclusion.
And this is exactly the tau perpendicular category by Hasso.
Yeah. It is. Yes.
Yeah. So, it's looking at their.
Yeah, but here, I think it's still different. This core shield thing.
But at the same time, this white
Mm.
subcategory, so that's so this white subcategory is the intersection of the torsion-free class.
Mhm.
So that's maybe why you get this symmetry. I don't know. Coming back to the point before, I don't know. Yeah,
I don't know. Yeah. So if you find,
Mm.
if you think about it and find something, tell me.
Yeah. Well, I will let you know.
Yeah, I don't know.
Yeah.
But I think there is something that needs to be understood. This is why I
Yes.
wanted to ask this question. I think we are missing something.
Right. Yeah, they have so many good properties, these lattice of torsion classes. But
yeah.
But it's very nice that you find it in this other very nice, interesting.
Yeah, it was quite a surprise to me. We tried because we knew the Tamari lattice was an example of transfer system. So we tried to look at other properties and everything worked.
Right.
It was like
yeah. And once again, AN appearing all over the place. I mean, this is this is quite surprising. Yeah. Yeah. Thank you very much.
Do we have any more questions? Well, doesn't seem to be the case, so let us thank Baptiste again.
thank you.